Think about what it would mean if we could build a machine that truly mirrored ourselves.
Hmm.
Not just, in appearance, but in how it moved, how it interacted with the world.
Hmm.
Could that be the ultimate proof that we really understand what makes us tick?
That's a fascinating thought. And yeah, that's pretty much the driving ambition behind humanoid robotics, isn't it?
It really is. And on
Wow.
this deep dive, we're getting into the nuts and bolts, quite literally, of the engineering challenges involved in bringing these incredible machines to life.
We've compiled a really interesting set of resources for you today. They focus specifically on the mechanical engineering hurdles in humanoid robotics.
Okay.
Our sources include some really in-depth looks at design and development processes from researchers at places like MIT, the Massachusetts Institute of Technology, and UCLA, the University of California, Los Angeles. Plus, some valuable insights gathered from the Semantic Scholar database.
Okay, let's unpack this ambitious goal then. Our mission for this deep dive is to sort of extract the critical engineering considerations. What goes into creating robots that don't just look like us, but can actually navigate and interact with the human world in meaningful ways.
Right.
We're going to explore everything from how these robots get around locomotion to how they manipulate objects and the underlying intelligent machine architectures that make it all possible.
Exactly. And a really fundamental aspect of how we humans interact with our environment is, well, walking on two legs. Bipedal locomotion.
Right.
This ability is just key for moving through all sorts of terrains, navigating complex spaces, and, crucially, freeing up our hands to do a million other things, carrying stuff, intricate manipulations, you name it.
It's almost mind-boggling when you stop and think about how we even evolved to walk on two legs in the first place. Our sources touch on a few leading evolutionary hypotheses.
Yeah, there are several ideas floating around.
One compelling idea is that freeing our hands was the primary evolutionary pressure, needing them for tools, carrying food. Another suggests that changes in our environment, like the expansion of savannas, favored the increased range and maybe efficiency that bipedalism offered.
Right, covering more ground.
There's even a fascinating theory about thermoregulation, the idea that standing upright helped us stay cooler in hotter climates, better air circulation, less direct sun hitting the body.
Interesting. What's really clear, though, is that while there's compelling evidence supporting each of these ideas, the exact reason why human bipedalism evolved, well, that remains an open question.
So no definitive answer yet.
Not really, but what we do know for sure is that our bodies have undergone pretty significant physical adaptations over the last, 4 million years, mostly driven by the need for energy-efficient movement on two legs. You could think of these adaptations as nature's engineering solutions, really.
And this is where it gets really interesting when we start thinking about robotics. We're talking about legs that are significantly longer relative to our torso. On average, our leg length is about 171% of our trunk length.
Wow, that much?
Yeah. Now, compare that to chimpanzees at around 128% and orangutans at just 111%.
Big difference.
Huge. We've also developed proportionally larger and more powerful leg muscles to support our weight and propel us forward. Our vertebral column is positioned closer to our hip joint for better balance. And of course, those incredible arched feet that act like natural springs, helping with energy transfer as we walk.
So when roboticists aim for human-like efficiency, these are kind of the biological benchmarks they're often looking at.
Exactly.
And when we analyze the mechanics of how we actually walk, it's essentially this elegant, alternating pattern of two types of motion. As one leg swings forward, it behaves much like a pendulum.
Right.
The other leg, the one touching the ground, acts as what's called an inverted pendulum, pivoting around the point of contact.
Okay.
It's a remarkably efficient and stable way to move.
It truly is. And it's a fundamental skill. We pick up pretty early. Human infants typically start taking their first steps around 11 months old. And as adults, our average walking speed clocks in at about 5 kilometers per hour. Now, the challenge for engineers is how do you replicate this seemingly effortless movement in a machine?
Precisely. And early attempts at creating bipedal robots were absolutely crucial in laying the groundwork. One notable example from back in 1984 is Waseda University's WL-10RD.
Okay, WL-10RD.
Yeah. This robot was a significant achievement for its time. It was capable of forward, backward, and even sideways walking.
Pretty good for 84.
Definitely. It was controlled by a, well, relatively advanced 16-bit microcomputer for the era and used rotary servo motors at its ankles, knees, and hip joints. It even incorporated torque sensors for basic feedback and had a laterally bending upper body to help with balance.
So it could shift its weight side to side.
Exactly. Its step turnover rate was about 1.3 seconds per step. So while not nearly as fluid as human movement, it really demonstrated the core principles.
That does sound impressive for the early days. But the sources also make it clear that moving from those, carefully controlled lab environments to the messy, unpredictable real world, that's a monumental leap.
Oh, absolutely.
We really saw this highlighted in events like the DARPA Robotics Challenge, DARPA being the Defense Advanced Research Projects Agency.
Right. Those challenges were eye-opening.
Even seemingly basic locomotion on uneven terrain or through obstacles proved incredibly difficult for many of the robots. DARPA's goal, of course, is pushing tech boundaries for national security.
That's a key point. The DARPA challenges really hammered home the need for a fundamentally different approach to humanoid robot design, especially for achieving dynamic motion, the kind of quick, adaptable movements humans make without thinking about every single step.
Right, like reacting to a stumble.
Exactly. One of our sources delves into a brand new humanoid platform designed specifically with this dynamic motion goal in mind. And a central feature of this design is the use of custom-designed proprioceptive actuators.
Proprioceptive. Okay, so that means these actuators can sense their own internal state, like they're the position, speed, the forces they're exerting. It's like the robot having a sense of its own body.
Precisely. And these actuators in this new platform also integrate liquid cooling systems.
Ah, cooling. Always an issue with powerful motors.
Yep. To effectively manage the heat that's generated when they're operating at the high power levels needed for dynamic movements. Now, if we look at traditional humanoid robot legs, they often have 6 degrees of freedom, or doof, per leg.
It's 6
It's typically hip yaw, turning left-right, roll, tilting side to side, and pitch, bending forward-backward, then knee pitch, bending, and ankle pitch, pointing the toe up down, and roll, tilting the foot inwards outwards.
Got it.
In humans, that ankle pitch is really crucial. It provides that final push-off, boosting energy efficiency at toe-off during walking. But replicating this effectively in robots with rigid, flat feet has proven to be a really significant challenge.
So some designers are thinking maybe simplify the ankle joint.
Precisely. To cut down on both the weight and the inertia, that resistance to changes in motion at the very end of the robot's leg, some designs, like the Artemis robot discussed in one of our sources,
Artemis.
they opt for a reduced number of angle degrees of freedom. This approach aligns more closely with what's known as a spring-loaded inverted pendulum model.
Spring-loaded inverted pendulum, like a pogo stick.
Kind of, yeah. It describes how our legs behave during walking and running, essentially acting like a springy strut, storing and releasing energy with each step. In the Artemis design, they actually use only ankle pitch. Simplifies the joint considerably.
That's a really interesting simplification. What about the hip joint? Is the alignment the same as in humans?
Not quite. In humans, the axis for hip yaw and roll are generally aligned with the main axis of our body. But in Artemis, the hip yaw axis is aligned vertically, and the hip roll axis is aligned with the sagittal plane, that's the plane dividing the body into left and right.
Why the change?
It might seem subtle, but it's a strategic design choice. It allows for more compact packaging of the actuators around the hip, and importantly, gives a greater range of motion specifically for the hip pitch joint, which is critical for swinging the leg.
Okay, clever packaging. And to further cut down on the weight and inertia of the legs, they've used mechanical linkages to move the heavy actuators closer to the body, right?
That's a really crucial design innovation. In Artemis, the actuator for the knee is positioned, so its axis is coaxial, shares the same axis with the hip pitch actuator.
Oh.
And similarly, the ankle actuator is located much closer to the knee joint than in a typical human leg. This more proximal placement of the heavy actuators significantly reduces the inertia of the lower leg segments.
The parts swinging back and forth.
Exactly, the parts furthest from the body. This is absolutely vital for achieving quicker movements and better overall energy efficiency. Think of it like swinging a weight close to your body versus swinging it way out at arm's length. Closer is easier to move fast.
Makes sense. The source mentions a parallel 4-bar linkage being used for the knee joint in Artemis. What are the advantages of using that kind of mechanism?
The parallel 4-bar linkage offers a few benefits. It allows for a simpler overall mechanical design, and it's inherently robust, which helps avoid what are known as singularities.
No singularities.
Yeah.
Those are bad configurations in robotics, right, where you lose control.
Exactly, where a joint loses one or more degrees of freedom, making control difficult or impossible. However, this simplicity does come with a trade-off here. A slightly reduced range of motion for the knee joint, around 140 degrees in Artemis.
Okay.
But the linkage itself is engineered to withstand very significant forces, something like 15 kilonewtons. And ensuring that linkage doesn't buckle under load is a key design consideration.
And to keep the leg structures themselves, like the femur and tibia, light but strong, the researchers used topology optimization. That sounds pretty advanced.
It is indeed. Topology optimization is a sophisticated computational method. It lets engineers figure out the absolute optimal way to distribute material within a defined space to meet specific goals, like minimizing weight while maximizing stiffness.
So the computer basically designs the most efficient shape.
Pretty much. Once these lightweight yet strong designs are generated, the researchers use parametric design software to create detailed manufacturable models. And these are finally produced using CNC machining computer numerical control, which is a highly precise process where tools remove material to create the final part.
Okay, so that's a really detailed look at tackling the challenge of making humanoid robots move like us. Now let's shift focus a bit to how they interact with the physical world, robotic manipulation and dexterity.
Right, another huge area. And we've seen incredible progress here over the decades. The Cato Laboratory at Waseda University made some groundbreaking contributions quite early on, between 1969 and 1983.
Wow, going way back.
Yeah, they developed a series of increasingly sophisticated robotic arms and hands, culminating in the remarkable Waseda Arm Hand 7, or WAM 7.
WAM 7. Whiskey Alpha Mike 7. What made it so significant?
Exactly. WAM 7 was a major leap forward. It used electrohydraulic actuators known for high power output, and it incorporated torque feedback at every single joint using strain gauges.
So it could feel the forces it was applying.
In a way, yes. It allowed for very precise control of the forces. It also integrated basic visual sensors, enabling vision-guided manipulation. In total, WAM 7 had an impressive 21 degrees of freedom, 7 in the arm, 14 in the hand.
21 Dolph, that's a lot.
It is. And the fingers were actuated by cables connected to motors in the arm, much like the extrinsic muscles in a human hand.
That sounds incredibly advanced for the early 80s. What kind of things could it actually do?
It was capable of a surprisingly wide range of actions: opening doors, painting complex curved surfaces with a brush, even playing a keyboard instrument at about 15 keystrokes per second.
Playing a keyboard.
Correct.
Seriously.
Yeah. Now, it's important to note many of these skills were achieved through largely pre-programmed sequences. But it was still a very compelling demonstration of the potential for robotic dexterity.
Still impressive.
And earlier models from the same lab, WAM 1 and WAM 2, used simpler electrical actuators. WAM 2 even demonstrated basic feedback control for grasping and transporting small objects, so you can see the iteration, the progression over time.
Right. Fast forward to today, and we have examples like the shadow dexterous hand. That one's specifically designed to be superhuman-like, isn't it?
It is. The shadow dexterous hand is meticulously engineered to closely mimic the dimensions and functionality of an average human male hand. It weighs about 3.9 kilograms and features an incredible 24 degrees of freedom.
24.
Yeah, the goal is really a general-purpose manipulator, something capable of doing almost anything a human hand can.
And the sensory capabilities in these modern hands are also getting incredibly sophisticated.
Absolutely. Take the Ishikawa manipulator, for instance. It incorporates a column parallel high-speed vision system. This system uses a 128 by 128 array of photodetectors that can capture images at an astonishing 1 kilohertz. That's 1,000 frames per second.
1,000 frames a second.
Yeah. And it actually uses 2 of these systems working together for accurate 3D targeting. And the shadow hand itself, it's equipped with high-speed tactile sensor arrays made from a pressure-conductive rubber.
Tactile sensors, like artificial skin.
Sort of. These sensors are on the undersides of the fingerlings. They're super lightweight, about 0.2 grams per square centimeter, and they can also sample tactile info at 1 kilohertz.
So you've got this incredibly complex mechanical hand, plus really intensive vision and touch sensing. Integrating all of that must be a massive engineering challenge, just getting it all to work together.
It absolutely is. Our source points out that this seamless integration of complex mechanics with advanced sensory input is a critical engineering hurdle for the next generation of humanoids. The ability to process and act on all that rich sensory data in real time, that's likely what will define their future capabilities and allow for truly intuitive interaction.
Now, all this sophisticated hardware needs, well, a brain to run it. The sources talk about something called the Intelligent Machine Architecture, or IMA. What exactly is that?
The Intelligent Machine Architecture, IMA, is basically a software framework for controlling complex robots. It uses an object-oriented approach.
Object-oriented, like in software development.
Exactly. It uses modular descriptions to represent the robot's hardware, the tasks it needs to do, and the environment it's in. A key feature of IMA is that it provides two distinct levels of abstraction, which helps simplify the whole control problem.
Okay, 2 levels. Let's break those down. What's happening at each level?
Right. So at the higher level, IMA uses a multi-agent network. In this network, the robot's various capabilities and resources, like a physical arm, a camera, or even a computational skill like vision processing, are represented as individual software agents.
Okay, agents.
These agents are then connected by defined relationships that describe how they interact and share information. Then the lower level of IMA is where these abstract agents and relationships are actually implemented using component object software modules.
Component object modules.
Yeah, in the specific example in our source, these were based on Microsoft's Distributed Component Object Model, or DCOM. So IMA essentially creates this network of independent software modules that communicate and cooperate to control the robot.
And how does that kind of architecture specifically help with controlling a complex humanoid robot that has tons of different systems and sensors?
Well, IMA facilitates what's called coarse-grained parallel processing, because the agents are relatively independent and communicate mainly through message passing.
Sending messages back and forth.
Right. And because DSCOM lets software objects run on different computers but interact as if they're on the same machine, different parts of the robot's control system can operate simultaneously and asynchronously. This distributed approach makes managing the complexity much easier compared to trying to write one giant single control program.
That makes a lot of sense. Modularity and distributed processing seem essential for tackling this complexity. The source also says IMA helps make the control system more robust. How does it do that?
Robustness in IMA comes largely from encapsulation. Each agent sort of bundles up a specific resource and all the software logic needed to manage it.
Okay, self-contained units.
Exactly. This means changes or experiments within one agent are less likely to mess things up or cause failures in other parts of the system. The high-level multi-agent network acts like a protective layer around the inner workings of each agent.
So developers can tweak one part without breaking the whole thing.
Pretty much. They can refine algorithms within an agent without worrying too much about destabilizing the entire robot. Plus, the architecture allows for flexible configuration, even potentially modifying things while the robot is running.
Okay, so IMA provides the software structure. What about how the robot perceives the world? The sources detail specific sensors used with the robot called ISAC, which use this IMA.
Right, ISAC. That stands for Interactive System with Active Cognition. It was a humanoid platform used to demonstrate IMA's effectiveness. In terms of sensors, it primarily relied on vision and audio.
Vision and audio, okay.
For visual processing, ISAC used color modeling. This involved a statistical procedure in a 2D hue saturation, or HS, color space. Basically, for an object they wanted to track, they defined an elliptical region in this HS color space based on its typical colors.
And ellipse based on color.
Yeah. Any pixel in the camera image whose hue and saturation fell within that ellipse was tagged as foreground, likely part of the target object. To clean this up and reduce noise, they also used something called morphological opening, a specific sequence of image processing steps.
So that's how IS could pick out objects based on color. What about detecting movement?
For motion segmentation, ISAC used a fairly straightforward method. It looked at the difference in pixel values between consecutive video frames.
Frame differencing.
Exactly. If the change in brightness or color at a pixel was above a certain threshold, it was considered part of a moving object. To minimize noise, they'd first blur the image slightly and then downsample it, reducing the resolution. The location of the moving object was then estimated by finding the center of mass of all those changed pixels.
And ISAC had actual eyes cameras on pan-tilt units, so it could actively look around.
Yes, it had a pair of high-speed, high-accuracy pan-tilt units that could independently control the pan, horizontal, and tilt vertical angles of its cameras. The system could precisely control position, velocity, and acceleration for each camera.
So it could perform sophisticated eye movements.
Absolutely. Things like smooth pursuit, where the cameras track a moving target to keep it centered in the visual field, the fovea. If the target moved out of this central area, the system would trigger a saccade, a rapid eye movement to quickly recenter the target. These movements were governed by math formulas calculating the motor adjustments needed based on the target's position and velocity.
So the robot could see and actively track things. What about hearing and locating sounds?
ISAC had a dedicated sound agent for that. It could detect the direction of a nearby sound source. First, it would filter out background noise by only responding to sounds above a certain intensity.
Okay.
Once a loud enough sound was detected, the sound agent could figure out the horizontal angle to the sound's origin, though with a fairly coarse resolution of about 15-degree intervals. This directional info could then be used to turn the robot's head towards the sound.
And all this sensory information, the visual focus from the cameras, the sound direction that would feed into the higher-level control system to guide the robot's actions.
Precisely. The head agent in the IMA architecture acted as the central coordinator for these sensory motor loops. It would get the focus of attention from the camera agents and decide whether to initiate smooth pursuit or a saccade.
Making decisions based on sensor input.
Right. And crucially, based on the final pan and tilt angles of the cameras once they'd fixed on something, the head agent could also calculate the estimated 3D Cartesian coordinates of that object in the robot's environment.
What about actually interacting with objects? The source mentions a hand agent with different grasp types.
Yes, the hand agent in ISAC could do two main types of grasps. A fast, pre-shaped grasp that didn't necessarily involve fine control of individual fingers, and a slower but much more precise grasp using the dexterity of the powered fingers.
Fast versus precise.
Exactly. Which grasp to use was managed by a finite state machine, a simple computational model that switches between states based on input. The hand also had proximity sensors to stop it from trying to grasp thin air.
Smart. And the arm agent would handle the physical movement to reach for these objects.
Correct. The arm agent calculated the necessary joint movements for the arm. It could accept goals either as Cartesian coordinates in 3D space or as a specific set of target joint angles. This gave flexibility to the higher level control.
So ISAC could put it all together.
Yeah.
React to sounds, visually recognize objects by color or motion, and do reach and grasp actions. That's a pretty solid demonstration of basic interactive skills.
It really was. The demo showed ISAC turning its head towards sounds, tracking objects visually, and successfully performing grasps, sometimes even sequences of them. As we mentioned, a finite state machine handled the grasp control, and a separate trajectory agent planned the smooth arm movements.
The source also briefly mentions McKibben air muscles. What are those? How do they fit into humanoid robotics?
McKibben air muscles are a really unique type of pneumatic actuator. Imagine an inflatable bladder inside a braided mesh sleeve.
Okay.
When you pump compressed air in, the bladder tries to expand, but the mesh forces it to contract lengthwise, like a real muscle pulling.
Contracts when inflated. Interesting.
Yeah. A key characteristic is their inherent compliance. They're naturally springy because of the compressible air in the elastic bladder. They're also relatively lightweight and have a high force-to-weight ratio. This makes them potentially attractive for applications where you want a more organic, compliant, maybe safer movement.
Interesting. A totally different approach to generating motion than electric motors. And the source also touches on sensory motor coordination, or SMC. What's the core idea there?
The basic idea behind sensory motor coordination, SMC, is that sensory input and motor output aren't processed separately. Instead, they're deeply linked and form distinct patterns or clusters in a kind of theoretical state space.
Clusters in state space.
Yeah. Each cluster corresponds to a fundamental behavior or a competency module, a specific action reliably triggered by certain sensory conditions. So an SMC cluster is essentially a learned mapping between specific sensory input and the corresponding motor output, letting the robot react appropriately.
That sounds really important for developing more adaptable, maybe even intuitive, robot behaviors. Now, switching back to the physical hardware, the source from UCLA really hammers home the critical role of actuators in enabling dynamic motions.
Absolutely crucial. And they highlight a big shift towards developing and using proprioceptive actuators for these demanding applications.
Right, the ones that sense their own state.
Exactly. The key advantages are high power and torque density, lots of force in a small package, low reflected inertia, making them easier to control precisely, and high transmission transparency.
Transmission transparency. Remind me what that is again.
It's basically how well you can feel external forces back through the gearbox to the motor. It's crucial for accurate force control and also helps the robot be more resilient if it gets bumped or hits something.
Got it. And the design priorities for actuators in legged robots are pretty different from, say, actuators in electric cars or factory robots.
Totally different. For EVs or industrial arms, you often want high efficiency at sustained high speeds. But legged robots typically operate at lower average speeds, but need bursts of very high peak torque, maybe 4 times the average torque for dynamic moves like running or jumping.
Ah, short bursts of power.
Exactly. Standard off-the-shelf motors can struggle with this because of something called stator magnetic saturation, which limits their instantaneous force output. This often means designing custom motors optimized for these high torque pulses.
The source gives a formula for the motor constant Carivim, relating torque production to power loss. What's the key engineering takeaway from that?
The Karim formula really highlights how much the motor's physical dimensions matter, especially the air gap radius, the space between rotor and stator, and the axial length of the magnetic core.
Bigger radius helps.
Significantly. Increasing the air gap radius, even a bit, can drastically reduce the gear reduction needed for a target peak torque and reflected inertia. Less gear reduction means much higher overall efficiency and better transmission transparency in the gearbox. The source gives an example where quadrupling the air gap radius could potentially drop the needed gear ratio from, say, 128.1 way down to 8.1. Big difference.
And this design idea prioritizing a larger air gap radius that's directly seen in the custom motor for Artemis's hip and knee pitch joints, the one with the big 90mm radius.
Exactly. Maximizing that air gap radius was core to their design. This motor also uses an outer runner configuration and has 40 pole pairs. The source provides a detailed table with specs, 890 grams weight, 45 Newton-meter stall torque, its torque constant.
Okay.
They even include a graph comparing its peak torque density to commercial motors and motors in other legged robots, and the Artemis design shows a significant improvement.
You mentioned transmission transparency again and how vital it is for dynamic robots.
Yeah.
Can you expand on why it's so critical?
Okay, so transmission transparency is all about how well an external force applied at the joint can be sensed back at the motor. In dynamic robots using proprioceptive torque sensing, where the robot estimates force by measuring motor current, high transparency is essential.
Right. Needs to feel the force accurately.
Exactly. If the gearbox has lots of friction or a really high gear ratio, it masks those external forces. It becomes super hard to accurately sense and therefore control the actual torque at the joint. The source compares a high-reduction off-the-shelf actuator with their custom low-reduction motor, showing a much cleaner, more direct relationship between motor torque and backdriving torque in their custom design.
And to make these custom actuators easier to integrate, they put the motor driver and controller electronics right into the actuator unit itself.
Yeah, a really neat integrated approach. It offers big advantages in modularity and cuts down on wiring complexity massively.
Fewer wires is always good.
Definitely. The custom driver board includes a powerful STM32F446 microcontroller running at 180 MHz, a smart motor driver chip from TI, a dedicated 16-bit ADC for precise current sensing, a thermocouple to monitor motor winding temperature, and an isolated RS-485 communication bus.
RS-485 for communication.
Yep, allows robust, high-speed communication back to the main computer at 8 megabits per second. By integrating all this, the only connections needed are main power and the communication bus. Really simplifies the robot's overall wiring.
And this embedded controller inside the actuator handles all the low-level stuff. Current, velocity, position control.
Exactly. It runs a sophisticated control algorithm called field-oriented control, or FOC, at a very high frequency, 22 kilohertz. FOC ensures that linear relationship between motor current and torque output, which is crucial for accurate proprioceptive control.
Okay.
It also tackles cogging torque, that slight unevenness you can feel in some motors, using feed-forward compensation based on a lookup table calibrated for each rotor position. This smooths out the torque delivery significantly.
Generating all that power in a compact actuator must create a lot of heat, though. How did the UCLA team handle thermal management?
Yeah, joule heating heat from electrical resistance is a major issue, especially with these low gear ratio actuators that tend to dissipate more heat. For Artemis, they built a direct liquid cooling system right into the actuator housing with internal coolant channels.
Liquid cooling, like in a performance PC.
Pretty much. They even developed a lumped mass thermal model to analyze heat generation and transfer to optimize the cooling. The source mentions they also looked at air cooling and immersion cooling, comparing the impact on thermal resistance and the continuous torque the actuator could sustain without overheating.
So, highly specialized, integrated, liquid-cooled actuators. What about the rest of the Artemis system? What sensors does it use to perceive the world?
Artemis has a pretty comprehensive sensor suite. It includes stereo vision cameras, specifically the ZED2 camera, which has a wide field of view and its own built-in inertial measurement unit, or IMU.
ZED2.
It also uses additional high-precision microstrain IMUs for more accurate sensing of its own motion and orientation, and critically, it has those custom-designed contact force sensors in its feet.
Ah, yes, the foot sensors. Tell me more about those again. They sound vital for dynamic movement.
They really are. The custom design uses small cantilevered beams with strain gauges. When the foot hits the ground, the beams deflect slightly, and the strain gauges measure this, allowing calculation of forces in 3 axes: normal, vertical, medial lateral, side to side, and fore-aft, forward backward, at both the heel and toe.
Heel and toe sensing.
Yep. They also use Hall effect linear encoders to measure beam displacement, and as a safety feature, they have wire EDM electron discharge machine retention features for overload protection. It's a design prioritizing robustness for impacts, maybe sacrificing a tiny bit of ultimate accuracy compared to standard force-torque sensors.
And running all the sensor data and the complex control algorithms needs serious onboard computing power. What did they choose for the main computer?
Good question. The selection involved balancing performance, power, and future upgrades. They initially looked at an Intel NUC Next unit of computing with an 11th gen Intel chip and an RTX 2060 GPU.
Okay.
But they ultimately went with an HP Elite Mini 800 G9. This offered better performance with a 12th gen Intel processor and an RTX 3050 Ti GPU. More processing power is key for things like handling the stereo vision data.
And easier future upgrades, too.
Exactly. The HP Mini had a consistent form factor across generations, simplifying future hardware swaps. The source even compares the specs cores, speeds, memory, GPU, weight.
Powering all these high-performance bits needs a solid power system. Custom batteries, I assume.
Yes, definitely a custom power system. Includes their own lithium battery packs, a sophisticated battery management system, BMS, for safe charging and discharging, and even a custom BMS-compliant charger.
BMS is crucial for lithium batteries.
Absolutely. Each battery module is designed to be just under the FAA's 100 watt-hour limit for easier transport. They're easily swappable, though not charged on board. They use high-reliability SAMTech connectors, and the design allows connecting modules in series for potentially higher voltage later.
With a big, complex robot like Artemis, safety must be paramount. What about emergency stops?
Huge concern. Artemis has a custom wireless e-stop system. There's a receiver on the robot and a handheld transmitter for the operator.
Wireless e-stop. Good.
Yeah, allows immediate remote shutdown. Importantly, the transmitter also has a secondary safety button. Activating that not only cuts motor power, but actively applies a 3-phase short circuit across the motor windings.
Shorting the windings. Why?
It puts the actuators into a safe, highly damped state. Quickly stops motion, preventing damage if it was moving fast. Communication uses robust XB transceivers, 2.4 gigahertz or 900 megahertz, and the transmitter even shows robot battery status.
And providing power to the computer from the batteries requires a DC to DC converter.
Yes, a specific DC-DC converter module provides the stable 19.5 volts needed by the HP computer. They chose a commercial, high-efficiency 116th brick module for this.
Okay. Finally, ensuring fast, reliable communication between the main computer and all those actuators and sensors is critical. The source mentions a custom USB to RS-485 adapter. Why build their own?
They found that the communication link could become a bottleneck, limiting control performance. Standard off-the-shelf USB to RS-485 converters often introduce noticeable latency or delay.
Latency is the enemy of real-time control.
Exactly. To overcome this, they designed their own custom adapter. It has an onboard microcontroller that signals the conversion chip to return received data immediately, minimizing round-trip time. This custom solution achieved much higher communication rates, up to 8 kilohertz for one actuator, and over 1 kilohertz for all 12 lower body actuators together. The source includes a histogram showing the huge latency reduction compared to off-the-shelf options.
Wow. So after all that incredibly intricate design and engineering, actually building and testing Artemis must have been a massive undertaking.
Oh, absolutely a significant endeavor. They did a lot of the manufacturing and assembly in-house. That includes custom winding the motors and precisely machining the gears using wire EDM.
Machining gears in-house.
Yeah.
Impressive.
Yeah. Structural parts like the femur started as solid blocks of aluminum, some weighing 30 kilos before machining. Initial testing was done with the robot supported by an overhead gantry and lots of padding for fall protection.
Safety first.
Always. Early walking tests hit speeds up to 2 meters per second, which is pretty quick. They even implemented a running controller with a flight phase, planning parabolic trajectories for the center of mass. They did notice slight drift in the center of mass during flight, something to refine later.
That's already very advanced. Did any unexpected challenges pop up during this initial testing?
Yes, they did identify some backlash in the gearboxes, likely due to the tight tolerances from the custom wire EDM machining.
Backlash. Like a bit of looseness or play between the gears?
Exactly. It negatively affected the precision of actuator tracking and caused some noise when changing direction quickly. They suggest potential fixes like adjusting tolerances or maybe using ground-hardened gears in the future. But interestingly, despite this leg backlash, the overall stability and robustness of both walking and running were surprisingly well maintained.
Well, this has truly been a deep dive into the intricate world of mechanical engineering challenges in humanoid robotics. From understanding our own evolution of walking to the complexities of advanced actuators, sensors, and sophisticated control architectures, it's just abundantly clear how multifaceted and challenging this whole endeavor is.
Absolutely. Replicating human dynamic movement and nuanced interaction in a robot. It's a monumental engineering task, pulling expertise from so many different fields.
It really makes you think about the ongoing quest for these truly general-purpose humanoid robots and all the exciting advancements still on the horizon, not just in mechanics and electronics, but in areas like, cognitive behaviors, developing more natural ways for humans and machines to interact.
Indeed, it's a fascinating, rapidly evolving field, and this deep dive really highlights that critical interplay between the physical hardware, the mechanics, the electronics, the intelligent software controlling it all, and, well, our own fundamental understanding of ourselves as biological beings. It's all connected.